two preliminary things. First, I feel a little bad that I stopped you. I mean, Myrto had to stop just once you get to the good stuff, which was sort of answering all the questions about shipping. But she'll be back in the afternoon and she'll answer all the questions about shipping. The second thing was I was absent for a large part of the poster session because I was preparing my talk for 5 o'clock. So, I talked to a bunch of people just now, and I'll be around after lunch if you want to get me, and I'm happy to talk. Okay. So this paper, actually, I'm going to start a little bit with the problems here and then go to other notion of equilibria. And then I am going to skip through enough so I actually get to the example. Okay. Let me note that there's a lot of detail that goes into this dynamic stuff. Okay. And, Myrto gave you an overview of it. The thing we're going to miss most here, and we've done it, and it's been by a sort of decision. The econometric parts we're leaving out, okay, presumably, but they're actually reasonably important in many of this, okay? So if you were going to do this seriously, you should think a little bit about the econometrics, okay, which we're not going to do here. That's what I do primarily, but we're not going to do it here. Okay, let me go on now, then. So most of what we've been doing, and I'll give you a 1-minute introduction. This is from the methodology paper. Is we're developing tools to analyze market outcomes. And the common thread is just take the framework from theory and incorporate institutional background that's needed to make sense of the data. Okay? And then we use it. And the focus, usually in the institutional background, is putting in enough heterogeneity among different people and institutions. What institutions actually do. And then using the equilibrium conditions that come from the framework. So, the framework, the common aspects of the framework are each agent's actions affect all agents' payoffs. And at the equilibrium arrest point, like I said yesterday, agents have correct perceptions. I have to define what that means. And they're in some form of Nash equilibrium. Okay? So when we started doing this stuff, the difficulty in incorporating sufficient heterogeneity and the complexity of the institutions, it was different for the static stuff than for the dynamic stuff. Okay, the static stuff, it was actually pretty easy, and I think we made a lot of progress. It's being used all over the world. The dynamic stuff, not so much. Okay, so I'm going to go back to the theory now and discuss where the dynamic stuff sort of was problematic, at least the simplest, the standard dynamic stuff, okay? So the initial frameworks used by Eric and Drew and others, state variables evolved as a Markov process. So the state variables are like the capital stock, the quality of your product, the characteristic of your product. They evolved as a Markov process, usually a controlled Markov process, so I got to invest. And the equilibrium was some form of Markov perfection. That is, when I looked at the expected discounted value from the game, I'm doing the best I can given what everybody else is doing. Okay? So, I worked on that also. Okay? So, what sort of could we think went wrong? Okay? So, the Markov assumption, I think except in situations involving active experimentation or really new situations where policies are by nature transient, I'm learning, so my policy don't, okay? We're likely to stick with the assumptions that states evolve as a Markov chain. So just, it could be second order Markov instead of first order Markov or third order Markov, but Markov. Okay, so it could depend not only on the last period, but the period before. And when I'm talking about dependence, again, it's like what Myrto said. It's dependent on not only my own state, but the states of all my competitors, okay? And that's evolving over time, like a controlled Markov process. Okay, it could be second order, I don't care, okay? We're probably going to keep that assumption for two reasons. One, it's convenient, but it really fits data well, okay? And, the alternative, something that goes all the way back in history and is complicated in that fashion, it suggests real cognitive constraints, information access constraints, conditions of limited memory, things like that, which we think are in some sense a priori unreasonable. Okay? Moreover, we can bound unilateral deviations. There's mathematics on this. And we have conditions which ensure that those deviations can be made arbitrarily small if I put in enough history. Okay? So I'm going to keep with the Markov assumption. Okay? The perfection assumption is different. The type of rationality built into this, the perfection assumption, is more questionable. And I'm not saying it has, so when I say something's questionable, I don't mean, I said this like at the beginning, okay? None of our models are perfect, okay? You're just not, the world's just too complicated a place for that. The question is, what's the best approximation, okay? And it may well be that until now, or even maybe in the future, this is the best approximation we can deal with. But it's made us run into problems, okay? It's from applied side, from the side of Murto or me, it runs into computational problems just in complexity, okay? And from the agent side, from thinking about modeling the world, okay, it leads to a question. It's just so complicated that it leads to a question whether agents are really, whether we can approximate agents' behavior in a simpler way, okay? So that's where this paper starts, okay? So the question is, if we abandon Markov perfection, can we better approximate agents' behavior and in some sense enlarge the set of dynamic equilibria that we can analyze? Maybe I need water, but so the complexity issue, there are two aspects to it. One is, remember, I have to know my own state variables and all the state variables of all my competitors as well, okay? So there's it's just a large state space, a large number of things to know at any period, okay? Secondly, I've got to be able to compute my optimal policies, okay? And that problem is computational complex. So let me give you a classic example of a problem that almost nobody does, and for good reason, okay? So think of a model for cars, which I worked on the static version of this model, okay? So think of what's going on here. So if you really believed all the perfection stuff, there's a bunch of consumers in the United States, 120 million households, okay? And each one is solving a dynamic problem. Should I buy a car today? I have a car today, should I trade it in? Or should I wait for tomorrow? And tomorrow there'll be new cars and new prices, and I might want to wait and just drive my car today, okay? So that's a fixed point. That's a contraction mapping like John Russ contraction mapping. It's a little more complicated, but it is a fixed point, okay? And I decide what to do, okay? I have some perceptions of what cars will be there tomorrow, what prices the cars will be at, and I decide what to do, okay? So there's 120 million households that do that, and then General Motors is standing over here, and it's got all the information from the 120 million households, okay? And it's deciding on what cars to produce, and it also knows what Ford and Volvo and everybody else is producing, okay? And it computes a solution to their fixed point with Murto's solution to that fixed point, okay? But of course, once they get the answer to what they do, it's not going to be consistent. The perceptions over there were not consistent with this. Is that clear? So this becomes a doubly nested fixed point algorithm. This is, if you took the car market and you took it seriously, there's no computer that's going to be able to do this for the next 75 or 100 years. Okay, the complexity of this is just, it's amazing. And the amount of information that you have to hold is also amazing. Okay? So that's a durable good market, okay? I could do the same for, a network good market, okay, experience good market, be a little less complex for an experience good market. Experience goods are goods which I don't know my value for them until I try them, like prescription pharmaceuticals. So there are a lot of markets that look like that. Okay. Go ahead, I'm sorry.
Wouldn't they really have to take each household separately?
So I'm going to get to that. I'm going to get to what they do, what I think a better approximation is. But if you took Markov perfection seriously, full information Markov perfection seriously, that's what's going on. Okay? Now, again, we could do asymmetric. I'm going to come to all that, okay? But that's what's happening.
Well, but in such a context, it would really be reasonable to assume that the consumer don't punish each other, but the firm...
No, the consumer single agent problem is taking everything as given. It's still a contraction mapping. It's still a fixed point for each consumer. The consumer's not playing a game. He's just taking prices as fixed and doing his stuff. It's a retail market. Okay? Firms are setting prices. Consumers can either...
It would be in such a So the fact that there are so many consumers is really not.
How can you do that? You're sitting there, you're doing Ford Tauruses, okay? You put a lot of Ford Tauruses out on the market this year, the demand for Ford Tauruses next year goes to zero. How can I ignore dynamics? I cut the price of Ford Tauruses. I know they worry about it because I've talked to GM. But you cut the price of Ford Tauruses today, people buy Ford Tauruses today, they don't buy Ford Tauruses tomorrow. I got to take that in consideration when I'm making my decision.
No, that's what, but the fact that there are 120 million consumers, that's not really relevant. It could be.
Their perceptions are relevant.
What is relevant is how many different types of consumers there
Right.
are. If there
That's
are only
right.
a few types, the fact
That's
that
right.
there are 120 million
So
won't
fine,
really matter.
fine. So I need to know the distribution of holdings crossed with the characteristics of the family. Yeah, that's still, we're talking something that's very difficult to compute, okay? I mean, and when I said 50 years with the best computers, I'm not exaggerating, okay? So, okay. So one can ask the question, and this is probably the answer to that question, whether even though it's hard to compute, you might be able to learn about it from the data. So I talked a little bit about that yesterday. I want to go a different route today, okay? Okay. So the first obvious fix to this problem is that agents only have access to a subset of the state variables, okay? So the firms only know, that, like Elchanan was saying, the firms only know how many Fords are out there, how many whatever, stuff is out there, how many households hold a Ford, how many households, okay, and so on. Whatever they do, you specify. And the firms, they don't, the consumers only know a subset of things, and everybody knows a subset of things, okay? And so we get into asymmetric information equilibria because, you know things, you might know, the consumer knows things that I don't know as a firm. They're serially correlated, so there's an asymmetric information. I have to make a perception of what the consumers know and what my other firms know, okay? And so if we were going to do this seriously, okay, in a Markov perfect framework, we'd go to Bayesian perfect, okay? So does that help you by going to asymmetric information? So the answer, there's two sides to this. It helps you in one way. You have to retain less information, okay? On the other hand, the computational burden gets worse, much worse, because now I have to compute posteriors and make sure they're consistent with the actions of people, okay? And that ends up being a much harder problem than the first problem, okay? So that doesn't really get you out of the problem, okay? Again, we could come back to learning, and I will come back to it at the end, okay? So the rest of the talk, what I'm going to do is I'm going to introduce a notion of equilibrium that's less demanding than Markov perfect. It's the same spirit, but it's less demanding, okay? I'm going to show you how to compute this equilibrium. I'm not going to do estimation, though it's in the notes, so you can look at the notes. And I'm going to consider, so it's going to end up that Markov perfect is a special case of this. Okay, it's broader and simpler to use. Okay, but because it's a special case, Markov perfect has already got multiplicity in it, so there's going to be much more multiplicity. Okay, I'm going to show you one way around the multiplicity. Okay, or at least most of the multiplicity. And I'm going to, whatever happens, I'm going to get to the computed example because that's the I/O. Okay, so if I have to skip stuff in the middle, I'll keep time. And it's about dynamic procurement auctions. And the question is, how much information should the government agency that's doing the procure give the bidders? Is that clear? So I could either announce the winning bid, I could announce who won the bid, I could announce what were the bids of everybody. You have a set of, you have options, and the question is, what's the optimal thing to do? Okay, so that's going to be the example. And it's only a computed example, okay, so I don't have to worry about everything that Myrto worried about, okay, which is probably the wrong way to go. You got to start somewhere. Okay, so what do I want to do? What do I think? Yeah, I'll think a little bit about change. So I'm going to look only at rest points. Okay, so things that are in some sense a Nash equilibria. So that helps me because the strategies at the rest point satisfy some form of Nash condition. So in some sense, I'm doing the best I can given what my competitors are doing. And there's a sense in which that has to be consistent with what my competitors are doing. Okay, so I'm not doing something that's obviously wrong. But it leaves open the question of the form of the Nash condition. Okay, so here's what I think. This is where we started. This is Chaim Furshman and myself. Okay, we believe, and I think we should integrate it in the audience, the agents perceive that they're doing the best they can at each point. So they're going to try and do the best they can. Okay, and that these perceptions are at least consistent with what they observe. So that's going to be the restriction that I'm going to hold. Okay. It might be reasonable to assume more than this, and I'm going to later on, but I'm going to start with just this. So it might be reasonable to assume agents know more than just what they observed from the past, okay? Either because they experimented or because they know something about the industry that Ariel doesn't know, okay, or stuff like that, okay? And I'll come back to adding more information. Afterwards, it will help. Okay, so now formalization of the assumptions. So firms make decisions are based on an information set. So the primitive of my model is going to be a set of information sets, whatever I know, or whatever I know, and whatever you know, and whatever all the competitors. So that's going to be the primitives. There's going to be private information, so that's going to be Murtaugh's omega, which is, I'm going to give a slightly different definition to it, okay, but it's going to be omega. And then there's going to be public information, which is CT. So that's stuff that everybody knows, okay? There could be stuff in the middle. It would just make it slightly more complicated. That some people know and others don't know. Okay. I'm going to assume that the set of information sets, and there might be different numbers of actors in every period. So this is the information set of firm 1. This is the information set of the n-teeth firm in the teeth period. So it evolves as a finite state Markov process on J. So that gives me back to the Markov game. So we can ask when that happens, but I want to delay that. Okay. I'm going to say policies. So each firm is going to have a policy, or each agent is going to have a policy. I'm going to say it's MIT. And it's got to be a function of JIT, right? Because that's all I know, so I got to make my policy a function of what I know. Okay, and I'm going to assume that's finite, but if you wanted to do it not finite, you would just do what Murtaugh did in the Erickson Pakes type framework. So it's just for simplicity. I'm going to work with what we call a capital accumulation game. These are the games that Murtaugh was talking about. Okay, the definition of a capital accumulation game is that the evolution of my own state depends only on my own control. So why is it a capital accumulation game? Because to invest in capital or R&D, the evolution of what I learn or what I have in my capital stock depends only on my own stuff, not on what everybody else does. The example's not like that. It's going to be an auction. In an auction games, that doesn't. So what's happening in an auction procurement game is I have a stock of something. In this case, it'll be timber. Is that clear? And I'm bidding on a new lot of land every month. Okay, and the amount I bid, I also have a lumber facility which translates timber into lumber to be sold. Okay, and the evolution of my stock depends on whether I want a big enough stock to employ my lumber facility. Okay, that's the dynamics in it. Okay, and the evolution of my stock. So I bid into this market, this procurement auction. Is that clear? And whether I win or not depends on what the other guys bid. So the evolution of my stock depends not only on what I do, but what everybody else does. So this is a restrictive assumption, but it lets me show things easier. Okay, when we get to the auction example, I'll go around it. Okay, I'll show you how to get around it. Okay, so in this case, by the way, public information is used to predict competitor behavior. Right? I might not know your cost, but I know your bid last year. Okay, or your price last period, and that tells me something about your cost, and that's my signal. Okay, so the public information is going to contain the signals. Okay, the state of the system is just the information sets of the firms in the system, okay, and it lives on something. And if each of these are finite, and under certain conditions, you can show that the number of states are finite. Okay, so I'm going to tell you something about mathematics. But just a sec. It'll just take me 1 second. Did you have chalk, Myrtle? Did it go somewhere? Where is it?
It's stuck in the...
Oh, I get it. Yeah, it really is stuck.
There's some chalk right here.
Oh, thank you. That'll do. Thank you, Eric. So Markov chains have the following property, finite state Markov chains. And they actually, the way it works depends on the economics of the problem, but I'll explain it. So say I just had two states for a second so I can draw it. I'm lousy at drawing pictures. Okay? So I have state S1 and state S2. Okay? And it's finite, so it's a box. Okay? And there's dots in the box. Okay? So these dots are possible states. With a finite state Markov chain, it'll start somewhere and it will wander around and it'll eventually get into a recurrent class of states. Okay? And once it's in that recurrent class, it stays there with probability 1 forever. Okay? That's any finite state Markov chain. Okay? So let me just say, for dynamics, for all of industry dynamics, if you read the first chapter of Friedman's trilogy of books on Markov chains, it's enough. Okay, one chapter, first chapter, David Friedman's book, he has a trilogy on Markov chains. The first chapter is enough. Okay, it will tell you why all this happens. This recurrent class, okay, if you were doing like one of Myrtle's models, it'll depend on the characteristics of the industry. So for example, the example I use in class all the time is if I had a small market, is that clear? I'd only ever have a very small number of firms in the market because it couldn't support more firms than that. Is that clear? But as the market size grows, I'll get markets that can support larger and larger number of firms, right? But before I ever get back to a smaller number of firms, there'll be entry. Is that clear? Because the market will satisfy that. Okay? So there's only certain states that can, that you can start at a small number of firms, but it'll grow. So there's only certain states that can last. Is that clear? And those are the recurrent class of states. And that recurrent class of states will depend on what you feed into the demand system, what you feed into the cost system, and everything else. You just compute it. Okay? So that's what's going on. Okay. So you have to know that for what I'm going to do. Okay. Okay. So this is going to be finite state. So it's going to get into a recurrent class eventually. And once it's there, it stays there forever with probability 1. Okay? Okay. That is, there's no escaping it. Okay, the probability of escaping it is 0. Okay, so now I want to define my notion of equilibrium. Okay? So I'm going to introduce a concept, okay? Just a bunch of numbers, and I'm going to tell you what they have to satisfy. Okay? So these numbers are these W's, okay? And what the W's are, I'm at state Ji, so all I know is Ji. Is that clear? So I have to make my decision based on what I know, so I have to make it based on Ji. Okay? So I condition on Ji, and I have some policies that I could choose, in this case a finite set of policies. Okay? And what I need in order to do that is I need a perception of the it might be the wrong perception, but I need a perception of the expected discounted value of future net cash flows once I choose that policy. Because I'm going to choose the policy that maximizes my perception. So I need a perception. Is that clear? Okay. So that's what these W's are. And we're going to compute them. Okay? And I also need an expected profits today. Okay? And I'll show you how to get them. Okay. So our assumptions apply that each agent chooses an action which maximizes its perceptions. So it's going to choose the W. For any Ji, it's going to choose the M that maximizes that W. Okay? And for those states that are visited repeatedly, so those states that are in the recurrent class, okay, those perceptions are going to be correct. Why are they going to be correct? Okay? Because you hit them many, many times, and there's a law of large numbers that will apply. Okay? It's just an average. You take, I can get it by just taking an average, and I get it with probability 1 if I hit it enough times. Okay, good. So what does that imply from the point of view of the model? So it just if M star is the optimal strategy, it says, regardless of whether I'm in the recurrent class or not, okay, my WM star has got greater than my WM. Okay, those W's could be wrong, okay, but I choose the M that my perceptions say are right. Okay? And then what happens for all ji, which is a component of a state that's in R, that's in the recurrent class here, okay? They got to be right. Okay? What does being right mean? It means that my perception of the expected discounted value, which equals the perception of is my perception of expected profits plus my continuation value. So again, what's happening here? This is the profits I get this period, and I'm going to tell you what the condition on it is. And what this is just the value function that I get tomorrow, okay? Because tomorrow I have j prime I, and there's a distribution of j prime I given ji. This is what I know today. Is that clear? So this is just integrating out over tomorrow's value. Okay? Now, what's the conditions? The conditions are that the expected profits, okay, are that this is calculated with this distribution. What's this distribution? This is the empirical distribution that's in your data about where my competitors will be tomorrow given today. Okay? You see this many times. You saw lots of data, so there's going to be lots of data requirements. Okay? If I see this, there is an empirical distribution of what my competitors do tomorrow. Due to the, I don't know. It's a simultaneous move game say it's a pricing game. Okay? So it's a simultaneous move game. Okay? Everybody submits their price. I don't know your price when you submit your bid. Is that clear? Your price. Okay? But there's going to be an empirical distribution of prices. Okay? When I'm at JI, I face an empirical distribution of prices. I've been here many times. Okay? There were realizations of my competitors' prices in the past time. That's what this distribution is. It's the empirical distribution of in this case, the general thing is j minus I, but it's the empirical distribution of my competitors' prices conditional on where I am today. And they're going to be at different states because it's asymmetric information, so there's going to be a real distribution. Wait, let me just finish the thought, okay? And then this is the same thing, right? I've been at JI before. When I was at JI before, there was a bunch of random draws on where I went the next day. Okay? There is an empirical distribution. I can read it off the data. It's exactly this. Okay? And that's what I'm going to integrate out with. Is that clear? You can see where this comes from, an empirical guy trying to play theory. Go ahead.
So in A, in the optimality condition, you still keep the empirical distribution despite the fact that you are considering changing your policy, but you say it will not affect the distribution, the empirical distribution that you are using.
No, I'm not sure.
You need to update that. When you compute optimality, you say any other policy cannot do better.
Right.
Okay. So for M star, you have that computation. For the other alternative policy, if you change what you are doing, in principle, it should affect the distribution.
Okay.
Are you or aren't you?
Yes, I am, and I'll show you why. I'll show you what happens, okay? This is the source of the problem, if I understand you right. So I'm going to get to a problem, okay? And if I understand you right, it's the same problem. But if I don't understand right, you should tell me. Okay? Okay? Okay. So that's that. This is called this is what Chaim and I called experience-based equilibria. Okay? And it's very similar to this Fudenberg and Levine self-confirming equilibrium. There are differences, but the basic difference is they were doing sort of a repeated game, and I'm doing a dynamic game. So states evolve in my game, and that's going to cause different kinds of issues. Okay, in a second, which comes back to your issue. Okay.
But isn't the issue? Didn't you make an assumption that does not that rules out the issue he's raising? I mean, that your action does not affect the states of others.
Oh, yeah, but that's for simplicity. I can fix that. I'm going to fix it in the second part, okay? I want to show you it in a simple way because I want to show you actually how you compute it. Okay, the other computation, the only thing that goes different when in the auction example, for example, is the way I actually do the computational algorithm. Nothing else. The equilibrium condition stays the same. There's not, if you think...
If you're in a world where your action affects only your state, not the state of others, then your issue doesn't come up.
No, it does.
You must change. Come on.
Yeah.
If you change your strategy then you are going to get
This is the problem with giving a sort of basically an applied methodology paper to a theoretical audience. But it's good because this is the interaction that you sort of want. You want to mix theory with what we can do in empirical. It does affect other people's behavior, and you'll see the way I compute it.
He wasn't assuming that your action doesn't affect the others. It just means he would, in
Just
capital
the-
accumulation, you can affect you and only you affect your capital stock, but that affects other people, and their capital stock affects you.
Thank you, Eric. That was the way. That's what I should have said in the first place. What? Okay, that's exactly right. What?
Okay, okay.
That's exactly right. Okay, go ahead,
I
Eric.
had a question.
Okay. We're not going to go. What? Go ahead.
On the previous slide, if you could go back. So you have the fourth line.
This one?
No, fourth line. B. fourth
One,
line.
two. This one.
That's that one. So you have the empirical distribution. I'm sorry. It's farther. It's the next equation.
This
That
one?
So you have the empirical distribution. What's the empirical distribution of J minus I given Ji?
Right.
But you never observe J minus I.
No, but what I was, so I don't really need, so I should have said the signal on J minus I. So it's going to end up being the prices that you set in the games. Okay? So that's, actually I should fix it. I will fix that. Okay. I think later on it is fixed. So. Okay. Okay. So if I was going through the whole thing like I do in class, I would do a bunch of these things. I'm not going to do anything about estimation. I did want to show you a little bit about how you compute this. Okay? That's a big problem that Murto brought up, and it's slightly simpler here. I'm going to use what's called a reinforcement learning algorithm. I've used it before. And the advantage of it is it's a really learning algorithm. So you could think of perturbations to the environment and responding to those perturbations by this learning rule. It's like yesterday in a way. Slightly different learning rule. So I'm going to show you how to compute equilibrium, okay, in one of these models. So it's an iterative algorithm, so I have to have a location where the computer is today and then update it. Is that clear? So I need to tell you what a location is. So a location is a particular place, okay? And what's at that place, okay? It's a list, it's what's in memory at that place. A list which includes the perceived, this is iteration k of the computer. Okay, that's what k is. It's a list of these w's that I have at that time. Okay, those perceptions that I have at that time, which need not be correct. Okay? And the number of visits to each point, because the accuracy of the perceptions will depend on the number of visits that I've had there. It's like you're learning an average. Okay? So what I have to do is I have to update the location, okay, the perceptions, and then the number of times I hit that point. Okay? So I'm going to do each of those, okay, except for the number of times I hit the point. So this is what's called, in the OR literature, a greedy algorithm. I'll show you what that means in a second. But it's asynchronous. So most of the algorithms that you've used, say in macro or even in I/O, they're what's called synchronous. So what happens is they're all iterative algorithms. But what happens in those is you go through, you have a list of states, and you update each state at each iteration, and then you go to the next iteration. I'm not going to do that. Okay? I'm going to do like a learning model. The only thing I learned this iteration is what happened at this state that I'm at this iteration. Okay? So that's called asynchronous in that literature. Okay? And greedy just says when I'm at state JIK, okay, and I have perceptions WK, I choose the optimal. Is that clear? I choose what I think is optimal at that point in time. Okay? So I'm maxing over M's. Is that clear? So I just choose what I think is best. Might not be best, but I think it's best at that time. Okay? Then I'm going to take random draws on the outcomes conditional on M star. Okay? I chose this M star. That determines for me a probability distribution of my omega tomorrow, given my omega today. Is that clear? That's why I want to do just a simple one first. Okay? Everybody else goes to omega ik. And then there's a rule about what the aggregate information is. What new information is generated. So in the pricing game, I would also have now a vector of prices from this period, which would go into my CT. Okay?
Now the W is a vector of WIs, right? Each one has its own WI.
Right. Each one has its own W, but let me
Each one
say,
is
but I'm
updating.
right.
Is updating.
Yeah, that's right. Each one is updating on its own information, on what it gets. So it sees its profits, it sees what its J prime is. Okay, it updates based on that. I'll show you how we're updating in a second, okay? Okay, so the learning interpretation, this is what, this B should be, this is my price, okay? Okay, so I'm going to assume that's what the agents observe, some function of the other guy's control. So that's price for this case, okay? The agent knows, and the agent knows the primitives. It knows its profits, its profit function as a function of the prices of everybody else and the prices of me, like all the static stuff we just finished doing, okay, earlier in the course, okay? And it knows its transition function, okay? So typically you'd have to estimate them, but I'm going to assume the agent knows them, okay? So if it invests MI, it has a certain amount of capital stock today, it knows the probability distribution of the capital stock it'll get tomorrow, okay? So its ex post perception of the value it got this period, ex post, okay, is I know what my omega is. I know what my M was. I saw what the prices of everybody else was. This is an aggregate state like Murtaugh's demand states, okay? So I saw that. I could fit it in. For any policy, I can fit this in here, okay? And, the only thing my own state can do is translate my own capital. I know and I saw what everybody else did, whatever I saw, the C. I know where I would have been tomorrow had I done M, in probability-wise. Okay? So this says, look, I was here today, okay? I know I got a random draw on my value because there's an asymmetric information. There's a distribution of what my competitors are going to do. Is that clear? But I got a random draw on it. This is the profits I got from that random draw. Is that clear? And this is the future value, the continuation value I got from that random draw. Okay? Okay. So that's like a random draw from my expected profits. Okay? From my perception of expected profits. So how am I going to update my perceptions? Well, one way of doing it, there are many ways of doing it, and I'll tell you in a second. This is from Robbins and Rowe. This is one of the most beautiful math articles I've ever seen. It's like 6 pages and explains everything. Okay, so these papers that are easy to understand are wonderful. They're really wonderful. This is a 1956 article, by the way. So this is what it's doing. This is called stochastic integration by those guys. Okay, what it says is, look, I'm going to just update it like an average. Is that clear? So I'm going to take, say there were 4, and I've been here 4 times. I'm going to take 1/4 of my realization this time and 3/4 of the average that I had before. Is that clear? So you can translate that. That just says my increment in W is 1 over the number of times I've hit this point, visited this point, times the difference between what I realized and what I thought before. So if what I realized was greater than what I thought before, okay, I update a little bit. I make it a little higher. If it was less, I make it a little lower. Is that clear? And the way I make it higher and lower is through this HK. Let me say, so this, so the convergence proofs in this are just for single agent games. Okay, that's going to be a problem. But for a single agent game, it depends on how you do the weights. This will work, but it won't be good. Okay? The reason it's bad is because you don't want to weight the early on observations the same as the later observations, because the early observations don't have much information in them relative to the later observation. And it matters for the computational algorithm. Okay? It matters for how quickly you can compute things. Okay? And if you go into this literature, and I'm not going to do it, there's optimal weights and things. Really what you should do is you should keep throwing out early observations. Okay? So notes, what happens? Say I hit a fixed point. Okay? Say the expected value equals W star. Okay? So then in expectation, this thing is 0 and I don't update anymore. Okay, at least an expectation. On average, I'll get it right. Okay?
Look, you will always be updating because you're always getting one particular realization, but you're saying on average you're not updating.
Yeah, that's right. I'm sorry.
Yeah.
Okay. This is the good part about doing with theoreticians in the audience. So, I learned the right language. Okay, so I'm only really going to learn the equilibrium values on states in R. I know that any stochastic process, even if it was the wrong one, it's going to converge to some recurrent class and stay there. Okay, that's what Friedman told you. Okay, so if once I get into here, I'm only going to be hitting points in here anymore. Okay, and then you will, that will converge. By the way, so okay, that's one thing. Okay, so agents, so you could actually use this algorithm as a learning algorithm. You could be an agent. Okay, and this is how I update my perceptions. Okay, you'll eventually get to equilibrium values. Okay, now the eventually is the hang up. Okay, because the eventually takes a lot of time. Okay, so I'm going to show you that. But it is true that this is one learning, and this is called reinforcement learning in the reinforcement learning literature. Okay, okay. The interesting thing about this algorithm from an algorithmic point of view is it doesn't have what's called the curse of dimensionality. So what was the curse of dimensionality? The curse of dimensionality says if I have many state variables, okay, say each state variable can take on 10 values, and I have 5 state variables per firm and 10 firms, that's 50. That's 10 to the 50 states, okay? That's huge. And that's the computational problem. That's one of the two computational problems. Is that clear? And this kills it. Why does it kill it? Because in the end, you're only going to end up doing on the recurrent class. The economics of the recurrent class will tell you how many states there are. It need not grow in any special way, and I can give you examples where it doesn't grow at all. As you say, increase market size or other things. Okay. Typically it will grow, but it will grow linearly in the number of states and not exponentially, and that's a huge difference. Okay? Okay. The second thing is, the second source of the curse of dimensionality in this stuff is when I have to sum out over the future. So if I'm at different states, and every time I sum out, I could go to many different states in the future. Is that clear? And if the thing is rich enough that you can get to curse of dimensionality, here you totally get rid of that, okay? At every iteration, all you do is add 2 numbers. It doesn't matter how big the state space is, you just add 2 numbers. You add what you thought last time to some fraction of what you thought last time to what you got this time. That's it, okay? The problem is, to get it right, you have to hit it many times, okay? So that there's still this problem, okay? But formally, there's no longer any curse of dimensionality, okay? And you can do more than this, okay, if you were serious about it. I'm not. Okay. I should skip this, but I'm going to tell you what's going on, okay? So it doesn't necessarily converge to an equilibrium. Okay, this algorithm I just showed you, I don't know of a proof, except for when the game is zero-sum. Then there's a proof because zero-sum games become single-agent games if you play with them right. Okay? But in fact, we've had very few convergence problems with this, much less than any other thing, because the noise in it makes it converge. Usually non-convergence and cycling comes from a discrete jump somewhere in the system. Okay? But we do have a test based on simulation that can test whether something converged. Is that okay? So for an applied guide, that's enough. Okay? Because what I do, it's just like the existence problem. Does it exist for applied guide? If I compute it, it exists. That's the answer. And for this, whether I converge or not, I test it, it converged, it's converged. It's an equilibrium. Okay? Now, it's always up to an epsilon, so you can argue about that, and I'm not going to argue about it. Okay? Let me just tell you, the original tests on dynamic games were actually pretty complicated, and actually in the original article, not in this one, but in the original article on Econometrica by Paul McGuire and myself, it was the test that was the problem. And the reason is you did converge to a recurrent class. Is that clear? Okay. But the test, to test whether you satisfied the fixed point, I had to integrate out of it over everybody else. So the test took, increasing fractions of the time of the computation. Is that clear? As I increase the size of the market, the test, so I forget it, 12 firms in the market, it took something like 4 days to do the test and 1 hour to compute the equilibrium. Okay, so it became ridiculous. So this is a different way to do it in this paper, and it's pretty simple. All you do, I'm going to just explain it in words because I don't have that much time. Okay, so here's what you do. You start at different states and you simulate a sample path. Okay, you stop the computer somewhere. Okay, and you simulate a sample path. Okay. That sample path, no matter what you're doing, okay, no matter whether it's right or wrong, it's going to be a Markov process because you've programmed it as a Markov process. So it's going to enter a recurrent class, okay? So you do, I don't know, 1,000,000 iterations, okay? You stop, you do another 1,000,000 iterations, you see if, or you do a million iteration on top of that, to see if the recurrent classes are the same. Is that clear? That you throw out the first 5 million, you do 1,000,000 iterations, you do another 1,000,000 iterations, you see whether the second 1,000,000 iterations have the same, fall on the same states of the first 1,000,000 iterations. Eventually they will. When they do, you have a recurrent class. Go ahead.
Can it be the case that all the states are recurring?
Pardon?
Can it be the case that all the possible states
Yes,
are recurring?
it can. It won't be typically in economic problems for the kind of reason I told you, I just finished telling you, okay? You know, I said, you know, big markets will never get to very small market sizes in any recurrent way, okay? You know, cars, you know, there won't be a car with high miles per gallon and it's very large because it's just too costly for anybody to produce. Nobody will buy it at that price. Do you know, there's the logic in all of these arguments, that's from the economics. This is just algebra. Is that clear? And that's what the economics will drive the empirical work. And that's exactly what you want for empirical work. Right? You want the data to drive. You know, we have the theory concepts from theory and all of that, and we're very thankful for that, and we use them every day. Okay? But we want the data to determine what's the relevant assumption, what's the relevant functional forms, what's the relevant institutional detail. That comes from the data. Okay? And your knowledge of the industry, which I admit sometimes makes it boring to learn all the details about the industry, but that's the way life is. Okay? So you get these sample paths, okay? And the sample path, once you get into the recurrent class, it's going to hit the same points over and over again. Is that clear? Okay? So you can get both the mean of the time it hit those points and the variance. Because you see it many times hitting the same point, you get different values at that point. Is that clear? So I can take the difference between the average and the theoretical construct, this W that's the average of the discounted returns that I actually get, okay? And my perception that started, I can square that difference. That'll be the difference between my perceptions and what the theory says. And that square, okay, will be, just like always, the bias squared and the variance squared. It's just the mean square error, okay? Mean square error is bias squared plus variance squared. But I have an estimate of the variance. So I can take out the variance. I'm left with the bias. And when the bias goes to 0, you're at an equilibrium. Okay? And this is an L squared PR. You end up using what's called the invariant distribution, the number of times you hit all the points. Okay, that's all I'm going to tell you about that. Okay, you can look it up. It's in the notes. It's in the papers. It's easy. It's really very simple once you know what you're doing on the computer, which I don't, but my students do. It's fine. I was once, by the way, I'll tell a quick story. I was once at the Santa Fe Institute to do stuff for the National Science Foundation and evaluate stuff. And I remember this guy, I think he had a Nobel Prize, I don't know, he was a physicist. He had this blue chain on him that he always wear. I can't remember who it is. It's a famous guy. And he said, the time I didn't really like computation until I realized I never had to go to the computer. All his students could go to the computer, and then he was into it again. So I have a little bit of the same thing. Actually, I started knowing something, and then all my students knew more than me. So, okay, so that's it for testing. And I'm not going to go over estimation, but I do want to go over this. So this comes back to your point. Okay, so you tell me if I get it right or not. Okay. So I'm going to focus on the recurrent class now. Okay, there's a question about getting there, okay, and that's the transition question. We talked a little bit about it yesterday, and it really isn't a solved problem. But I'm going to talk about what happens in the recurrent class. So in the recurrent class, there are two. I'm going to classify the points in the recurrent class. There are two types of points, okay? One type of point, or I'm going to call interior, okay? An interior point is a point that can only transit to other points in the recurrent class, no matter what policy I take. Okay? So I might not take the optimal policy. I evaluate some policy that isn't the optimal policy. But even if I take it, I always land in a point in the recurrent class. Is that clear? So I get the values of that policy correct. Is that clear? Because I'm going to land in the recurrent class. I have the recurrent class correctly if I'm at an equilibrium. Okay? There are other points in the recurrent class that I'm going to call boundary points. Okay? So what happens at boundary points? If I'm playing the optimal policy, I get inside the recurrent class with probability 1. That's the definition of the recurrent class. It's in the recurrent class, so it has to be true. Is that clear? That's the definition of the recurrent class. However, there are feasible points that I could take that will take me outside of the recurrent class. Okay? Because the condition for me staying in the recurrent class is just when I play the optimal thing. Is that clear? If I played I could play a feasible policy that might take me outside of the recurrent class. Okay? The things that take me outside the recurrent class, those conditions I gave you, don't say anything about what those perceptions are. Is that clear? Okay? And different perceptions of what was outside the recurrent class can generate different recurrent classes. You know, if I think that it's not optimal to enter, even though it is optimal to enter, and there's nothing that tells me that it is optimal to enter because I never hit those points, I won't enter. Is that clear? So that's going to generate more multiplicity than in the standard Markov perfect stuff. Okay, because of this boundary set. Okay. So I'm going to tell you what we do about it. I'm not telling you it's the best thing to do about it, but it is something to do about it. You know, by the way, so the data can rule out some of the equilibria. Okay, you see some policies at some states, you know they were equilibrium policies, so at least you get inequalities from that. And sometimes you have external information. I'm going to now assume you don't know any of that. Okay, so you could do experimentation on the boundary. You could assume firms experiment on the boundary and learn stuff about outside the boundary. Okay, but I'm not going to do that. So this is from this new paper that it's just up on my website. So here's a stronger notion of equilibrium. It's actually the obvious thing to do. Okay. So we're going to assume that the perceptions are consistent with the results from actual play at feasible actions at boundary points. What does that mean? Okay. It means that when I get to a boundary point, okay, and I consider other play, I do have stuff in memory about the value of those other plays. They're the WKs. They're just not right. They're not equilibrium WKs, but they are WKs there. Is that clear? Okay. And it's going to be what it has to be true is that my policy at the Ji I am at, if even if it's the boundary point, has to lead to greater than my perceptions of what is outside of the recurrent class, which may be wrong. Okay? Okay, so that's the condition. Two things about it. One, it's an inequality condition instead of an equality condition. Is that clear? So it just says it has to be greater. It could be, it doesn't have to be equal. Okay, it's an inequality condition. Okay, so that leaves, still room for stuff. It also leads to a different kind of testing procedure because I have to learn how to test for inequalities. Okay, if I'm going to go back to the computer and do it. And the paper has a way of doing that. By the way, that's, one of the things that happened in econometrics that changed I/O. Okay, the ability to test for inequalities, because Drew Funberg, no, was it Drew? Somebody said, one of the theorists that I talked to said to me, when I said we now know how to do inequalities, he said that's all of theory, because what you're looking at is A greater than B is better than B. Okay, it took a lot of time for econometrics to do that, and the reason it took a lot of time to do it is essentially it's a discontinuous thing. I do A, I could have done B. Okay, it's not continuous in the parameters. At some theta, you jump from A to B. Is that clear? There's a policy function, and as theta moves, instead of going in, I go out. Is that clear? I don't go in. Okay, okay, and that changes econometrics. All the well, I don't know about all. I don't know what you've learned, but most of the method of moments, the general method of moments thing, is just all based on an expansion, and the expansions don't work anymore, and they really don't work. I mean, it's not like, this is a little issue. It's a big issue. Okay, and now we know how to do testing for this, but it would require a whole lecture, and I'm not going to do it. But you can find it. Actually, you can find it in my lecture notes from my class if you want it, and there are lots of papers on it by now. Okay. Okay. So this is, this is just telling you how to do it. Yeah.
Could I just ask about this? What happens if you find out that there are such M that you want to choose to go outside of R?
You're not at a good point. You're not at a boundary consistent equilibria.
Yeah.
Okay. So what you do is you increase the values for the points outside, and you keep running. Because once you increase the values for the points outside, you'll start moving there.
And
Okay.
then
You do the whole thing over again. Okay. And I'll show you. Okay. But can I just say that let me say one thing to answer that for a second. Where you start these W's matters. Is that clear? So you really want to start, if you really want to explore all options, you want to start very high. Okay, so as one thing goes down, you try something else until it goes down. Of course, by starting very high, it's going to take a long time for them to come. Okay, so that's the trade-off. Eric?
From what you were saying before, it sounds to me as though in practice you're not going to have interior points, because an interior point is one where no matter what you do, you stay in the recurrent set. But to use the example you were taking before, you could always change your policy to a large car which is very fuel efficient, no matter where you are. So that suggests that where you are can't possibly be interior.
It would have to be. You'd have to have perceptions which say it's profitable to move there to the large car with fuel efficiency.
No, I thought if you're interior, no matter what policy you take, even if it's not optimal, you will stay in the recurrent set. Here.
Yeah,
So
you have to have.
So if I switch to the large fuel-efficient car, I can always do that. That's always feasible. But it's never going to be profitable.
I'm thinking of the firm.
No.
Okay, the firm has a perception of its value from switching to the high fuel-efficient car. It knows its cost of producing them is too high, so it knows that its profits are too low. So its perception of what profits will be out there are too small. But let me take a step back, okay? Which is, in fact, when you start writing down asymmetric games, there are a lot of points that are boundary points, okay? And that's the reason we put on this restriction, okay? And it tends to work. I mean, I don't know. The ones we've computed work, okay? So, and if you start very high, okay, so I think we must have computed about 20 of these for this game just to look at the robustness of the answers. And we only found one because we started very high. It took a long time to compute. I'll show you in a second. But because we started very high, there was only one out of the 20 that wasn't boundary consistent. Okay? Because we checked every one of them. Okay?
I apologize. I have to go.
Okay, so I'm not going to do the economics, so you get to miss the economics.
I'm sorry.
It's okay. It might be worth missing. Who knows?
I wish I could stay.
So I want to do dynamic procurement auctions. Virtually all the empirical work on auctions has been static, so one-shot auctions. Okay. So if you thought of winning an auction to produce an aircraft or a ship or anything else, it depends on the backlogs or the order book of the firm. Like Murto was explaining, it's going to take you longer and it's going to be more expensive if you go to a shipbuilder who has a large book. Okay. Same thing with aircraft. If you're doing a timber auction, which we're going to do, or you're doing road construction, and these are things that happen periodically. In the timber auction, the timber companies that harvest the land also own lumber facilities. Okay, so their action in the auction is going to, how aggressive they are in the auction depends if they have enough timber today to satisfy their lumber facilities tomorrow. Okay, and a similar thing happens with roadwork auctions. They have machinery and equipment in place. Okay, they want to use it. Okay, and they want to make sure. Okay, so most of the auction literature, for procurements, it's a problem not to go dynamic if you think about it empirically. Okay, Okay, so here's the game. So again, this is a computational thing, okay? So I don't run into all of Murtaugh's problems yet, but it's only because I haven't tried, okay? I mean, if I went empirically, I would run into a bunch of these problems, okay? So here's the structure. There's an auction at the right to harvest timber on a parcel of land in each period, okay? Firms enter the period with a stock of lumber, their omega IT. They harvest, process, and sell at a fixed price, okay? So there's a international market for lumber, okay? They're going to sell it at 1 unit per 1 unit of lumber. The harvest and the processing outcome is stochastic. So I win a lot. The amount of actual lumber or valuable lumber on the lot is a random number, okay? And I send 4 guys out to harvest, and the amount they harvest depends on the weather and the roads and everything else, and it's random, okay? Firms decide whether to pay a fee and enter the auction, so that's F. And they simultaneously bid, okay? And they bid in discrete increments, okay? If there's information exchange between the firms, it occurs now, okay? Before the actual auction, okay? Then the outcome of the auction is announced, okay? The winner discovers the amount of timber on his plot. He sends somebody out, discovers the number of timber. Each firm gets a random draw on harvest processing, okay? FI, okay? And the winner is announced, and the bid, I never put this in, but the bid of the winner is also announced, okay? So that's a choice variable for the agency, okay? It could announce the bid, not announce the bid. Is that clear? Could announce everybody's bid, could announce who, and in this case, the people who entered in the auction are also information, okay? The firms can decide to, they have a, the firms have I forget what you call it, a trade association, and periodically they share their information, okay? So in some versions, they're going to share their information every 4 periods, in some version every 2 periods, okay? So and that's going to be one thing. And in one version, they're going to choose whether to share information, okay? Okay. And when information is revealed, it's truthful. I'm not going to worry about incentive compatibility of information, okay? So the profits of a firm, when its state is Ji and the competitor's state is J minus I, and it gets an epsilon and an eta, okay, are it's what it sells outside. Okay, so this is it's the minimum of omega I. So if it has timber, which is omega I, okay, if it didn't win the auction, all it has is omega I. It harvests E plus epsilon I. If it harvests as much as omega I, it takes omega I. If it harvests less, it just gets this, and it just sells it, okay? If it wins the auction, it has its omega I. This is an indicator function, so it's 1 when he wins and 0 elsewhere, okay? And then he gets additionally theta plus eta, and he could use that to sell on the auction. Is that clear? Okay, so that's the profits from the auction. This is going to be not capital accumulation, okay?
There is no resale,
No,
they cannot.
they sell it on this international market. Okay, this is all, a figment of my imagination, or Chaim's imagination. Okay, so it's not, but you want to go somewhere and see what's going on. Information sets. So that's a basic question we want to ask. What are the implications of different information structures in dynamic auctions? And do these implications depend on the extent in which we discount the future? If John were here, John's one of the Oscars, John Asker was here before, he would start telling you all about the difference in laws in the different countries of the world about information, okay, because he knows all of that, okay? But it is true that in Britain, the sharing of this kind of information would be called a restriction by object, and it's very close to a per se violation, okay? You shouldn't be doing it. Is that clear? In the United States, it's treated as a rule of reason, so depending on how strategic the courts depend, you're not supposed to share information, okay? So, we did collusion before. The way you prosecute a collusion case is you send somebody in with a tape recorder, and when they're sharing information, you tape it, and they're guilty. That's it, because it's a per se violation. It just says, if you're caught sharing information, you're guilty. Okay? And it doesn't matter whether it was good for the economy or bad for the economy. That's the rule of reason. Okay? Okay, so this is more like per se in Britain and more like rule of reason in the United States. Okay? And then, so I'm going to try different T's just to find out how much of the information is important and whether it's more important than was it important to include dynamics to understand this or not. Okay? And then I'm going to choose one where every T periods, and the T is going to be 4 for that one I'm going to play with. We ask the firms, do you want to share information? Okay, and they reply. Okay? And if they all reply yes, we share the information. If one replies no, we don't share the information. Okay? All is 2 in this context. Okay, so I shouldn't exaggerate. So information sets. So one thing you know is the amount of time since the last revelation of information. Okay, the winning bidder of the current period, and the winning bid, the identity of the winning bidder and the winning bid, the participation decisions of the other firms that didn't bid, whether they didn't win, that either bid or not, and okay, and your own omega. So CT, the way I update CT is if there's no information revelation, I have I have the information I had last period, and I update it by telling you who participated, what was the winning bid, who won, and what was the winning bid. And I get a new information set. Okay, that's the way public information evolves. If there is information, I find out the omega. If there's the trade association provides information, then I know everybody's last period omega. Okay, but I also get this period, who won this period. Okay, what were the winning bid and the tau t. Okay, the winning bid is irrelevant in this case, so I don't know why I put it in. Okay. So this is not a capital accumulation game. Okay? One agent's choice of control will affect the evolution of the other firm's states. Okay? So again, what's determining the evolution of states? Whether I win the auction or not. Whether I win the auction or not depends not only on my bid, but it depends on everybody else's bid as well. Is that clear? Okay. So it's not a capital accumulation game. This complicates the computation in the economics. So the economics of the computation, and an agent can refrain from bidding today or not bid aggressively today in order to let its competitor win today, so that tomorrow the competitor will be less aggressive because it's going to have a bigger stock tomorrow, and maybe it's better for me to win tomorrow than win today at a higher price today. Okay? So what's the value function? I have time. I probably skipped more than I should have. The value function is my perception of what I get if my JI and I don't enter the auction. Okay? So that's, I bid 0. Bidding 0 for me is not going into the auction. Okay? Or I enter the auction and I choose a B that maxes my perception of what I would get were I to bid different things in the auction at this period. Okay? And the profits are just calculated like an experience-based equilibria profits. Okay? So it's just, the actual expected profits are my profits given my JI and what everybody else does at their J minus I, but I don't know their J minus I, so I have a perception of that. Okay? And then there's an exogenous distribution of amount of timber on the land and amount of harvest I can do. Okay? So that's the theoretical concept, and the empirical concept will just put in the empirical distributions for these things. Okay? So if BI is greater than 0, the firms participate, okay, and they get the profits. This is how I update. They get the profits, okay, and if they win, they get the random draw on omega prime. It's a result of the eta of the random draw on the harvest. Is that clear? So I'm just doing my update now. I have omega I. Is that clear? If I win, I get an eta draw, and then I harvest, and there was an epsilon draw. Okay, so that's just my transition for omega. It's like omega t plus 1 equals delta omega t plus, okay, it's the same thing. And then there's some update determined by the rules I gave you here, okay, for C prime, okay, and that's C prime, and then you got to integrate out with respect to the exogenous distribution of, okay. And then if I don't win, which is probability 1 minus PW, okay, I don't get the eta, but I update the same way, other than I don't get the new timber lot, okay? And everything else is the same, okay? And then if I don't go into the auction, okay, I just get W0, okay? I don't get in, so I sell off what I can from my stock, okay? And I have the continuation value. Okay. Somewhere here I missed the cost of going into the auction. It should be in this. If I go into the auction, I forgot to put a minus GF here. The cost of going into the auction, the fixed cost. Okay, I apologize. I did this on the plane. So. Okay, parameter values. It's not that I didn't write the paper on the plane. I just took things from one paper, moved it to the other. Right, that's what I did on the plane. Yeah. Here are the parameter values. I'm going to show you now 3 equilibria. We computed many equilibria. Okay. One is the time between periods was 4 periods. One is the time between revelation is 1 period. Okay, so this is the question is, if you give guys more information, is it better or worse for the guys or for society? Okay? And then this is VIA, which is voluntary information exchange. Every 4 periods, we give these guys the choice. Do you want to share in the next 4 periods or not share in the next 4 periods? And you know that in 4 periods hence, you get the choice again. Okay? These are the parameters. I don't know that they mean that much to you. But in this model, the fixed cost, the one where I'm showing you, there's another one where the fixed costs are half of this. The fixed costs are relatively large. Okay, I forget what they are. They're about a quarter of the winning of what you get from the average sale. Okay? Here's some computational details. So you'll see that we haven't solved all the computational problems yet. Okay? These are the sizes of the recurrent class. So in the B equilibrium, that's every 4 periods we reveal. So remember, then I got to keep in memory what happened in the 3 periods since this period. Okay, that's all the winning bid, the participation decisions, and everything like that. Is that clear? That happened in prior periods. Okay. You get in the recurrent class, you get 325,000 points, but the number of points you hit in getting there is 8 million. Is that clear? So you hit 8 million. Okay, it shows you that the recurrent class is rather small relative to the number of states you try. Is that clear? But it also tells you that it's going to take a lot of time to find the 325,000. Okay? When you go to the information exchange equilibrium, it's much smaller. And why is it much smaller? Because I don't need to keep in memory what happened 2 years before, 3 years before. Each thing that I could possibly have in memory is another state. Okay, that's the explosion of states that happens in the curse of dimensionality. Okay? And then VIE, it's worse, a little bit worse. Okay? The computation times, to do 5 million iterations, it's about, on this machine, this was a laptop, but a good laptop. It's got these precision things. It took 1 hour, 38 seconds, 38 minutes to do 5 million iterations, and then another 1 hour, 40 minutes to check whether it was experience-based equilibria, to get to an experience-based equilibria, and then 3 hours to find out whether it was boundary consistent. Okay? So it worked out for this one. I looked it up just before I came. It took 6 iterations. Okay? So I did this and this 6 times before it accepted. Is that clear? So that's 3 hours, that's 18 hours, and you add 3, which is 21 hours. So that's still doable, but this is a very small problem. There's 2 firms, you know. So you can see, and this is just this is just our stuff that gets rid of many of the problems. Okay? And when you go to the IE is very easy. Okay? It took 16 minutes to do the boundary consistent thing. The voluntary information exchange was much harder also. Just before it converged, it took a lot longer, and the testing took, 75 hours. Okay, so yeah.
Did you consider how this would work if you want to break it up into parallel computing?
So Jihai did the computing. Okay, my guess is she paralyzed. There's only 2 guys.
Precision. So parallel is a lot more.
So let me just say, I'm not the computer guy in this group. Okay. Let me just say though, you think that it's just it's a detail. It is a detail of computing, but that's what's stopping dynamic analysis, because the conceptual stuff we're pretty well down. We took most of it from theory. We had to mix it up a little bit. Okay, it's pretty down, and it's super important. Okay, and it's the computing that's sort of stopping it. Computing and maybe a proper model of agents' behavior, cognitively. Okay, which is attempt at this. This is the attempt at that. Okay. Okay, so I want to show you a bit about the results because they're sort of interesting. I'm going to compare these two results too first. Okay. So when you do static auctions, the aggressiveness of the bidding and the number of people participating are correlated, okay? If it's a really valuable auction, there's lots of guys participating and the bidding is aggressive. Is that clear? So in the information exchange equilibrium, it looks like collusion, okay? At least if you look here, because they're bidding much lower and getting the stuff, okay? On the other hand, their participation rate is higher, which is not what you would expect from the standard static model. Is that clear? Okay. The total revenue that goes to, because the bids are lower, the total revenue that goes to the procurer, the agency, is less. Okay. But the firms earn more and when there's more information. Okay. And that offsets, and it's pretty much similar total surplus. Okay. If I was doing a statistical test, this wouldn't be different. Okay. The other thing I want you to note from this is a social planner problem, I'm going to skip it, is the VIE, the voluntary information exchange, is very close to the not so close to the information exchange one, closer to the one that doesn't information exchange, which says they don't want an information exchange. And this despite the fact that profits are higher in the information exchange one. Is that clear? Okay, so I have to be able to explain to you why that's happening. Okay, and that's what the rest of this is about. Okay, so this is why it's happening. Okay, so here's what I want you to notice. Okay, remember, information exchange generates higher value. Value is monotone in average profits, by the way. You can show that formally. Okay? Okay, so average profits are value. Okay? Information exchange generates higher value. Is that clear? But at almost every state, no matter where we are, these are just aggregates, weighted averages over when omega is less than 4 for both firms, just a weighted average of those states. Is that clear? I could have, if I put it all on that, you wouldn't see. There'd just be too much to see. Okay? So you can see that the profits are higher for the one that doesn't have information exchange, almost everywhere. So it's higher here. Here it's about the same. Here it's higher. Here it's much higher. Here it's higher. Here it's much higher. Is that clear? So almost everywhere it's higher when you don't give information exchange. Is that clear? Yet we know that the value is higher when there's information exchange. How can that happen? Well, it's obvious how it can happen. It can happen because the information exchange guys are at states where profits are higher more often. Is that clear? Profits are always higher for both of them when they have more timber in their lots. Is that clear? So what the information guy, and you can see that here. So the probability distribution of both guys being less than 4 is 65% when you're not sharing information. Is that clear? But it's only 32% when you are sharing information. Okay? And when you go down here to where the times when there's at least one firm with 5 to 7 are 20% of the time here and 12% of the time. When both firms are above, it's 6% here and 88%, less than 1% there. Is that clear? So you can see what's going on. What's happening in this model, okay, is that for some reason the dynamic incentives, when you have a lot of information, are putting you to states where you make a lot of money. Is that clear? But if you don't, and that's if you have a lot of it, but if you don't have that information, you don't have enough information to get there. Okay, and I'll show you how that happens now. Okay? here's the differences in policies. So all the numbers in black, okay, I don't know, I'm not very good with this particular tech program. So I had to put them together to get them on one page. Okay, some of you guys could have probably done this better, okay? But the dark ones are where the information exchange probability are higher than the other ones. So you can see here, it's not collusion, right? When they're at small states, nothing like collusion, they're actually more intensively bidding. Okay? So when they're at low states, the bids are much higher. When I have more information, I know you're in a low state and I'm in a low state, I bid aggressively. Is that clear? But when I'm in the B equilibrium, I don't bid so aggressively because I don't really know you're in a low state. You may be in a high state, and if you're in a high state, you're going to bid low. Is that clear? So I can win with a low bid. Okay? Okay, then when you go up here, okay, or even up here, okay, you can see what's happening in information exchange equilibria, okay? Well, what's happening is, well, especially like you either don't enter at all because I have a high state and I know the other guy has a pretty low state. Is that clear? Or I enter with a low bid in case he happens to have, in case the one period information was enough to put him up, okay? But you never bid high, okay? Whereas if there's not much information, you still bid high sometimes, okay? So that's what's generating it. Is that clear? If I don't have enough information, I don't know that you're low or high. So if I'm in a low position, I don't know whether to be aggressive or not. Is that clear? And if I'm in a medium position, I don't know whether I have to be aggressive to beat you or not. Okay? So I smooth my bids. Okay, that's the optimal thing to do. Okay? But if I know where you are, I know exactly what to do. Okay? Or I have a much better idea of what to do. So if I'm in a low state, and I know you're in a low state, and I want to get up there because all the profits are higher in the upper states, I'm going to bid aggressively. So are you. Okay? And if I know you're in a high state, you're in a low state, and I'm in a high state, I know you're going to bid aggressively. So I'm not going to bid aggressively, and many times I'll just drop out and let you win. Because I know I can't beat you unless I bid too high, and I already have stock to sell tomorrow. Okay, I don't need to win this time. Is that clear? And that's what's going on. Okay? So you could have never gotten this from a sequence of static auctions. Okay, you would have gotten it entirely wrong. Okay? So to see that more clearly, when beta equals 0, okay, so this isn't quite a static auction when beta equals 0. The only thing we do, we put the discount rate to 0, so I don't care about the future. But I do care about the past, because that's my information on what you have. Is that clear? But you can see even then, and there is a difference between this and a static auction still, you can see the information exchange equilibrium and the one that doesn't exchange information are pretty similar. It's the fact that it's dynamic and that I can save for tomorrow and I can bid aggressively today so that tomorrow I'll have stuff. Okay, and I cannot bid today because I know that tomorrow you will add up and I can bid less aggressively tomorrow. That's what's generating it. Okay? Okay, I'll do one more thing. I a little early, but maybe you guys have questions. So the information exchange equilibrium, what happens? So this is for the voluntary information exchange equilibrium, and I'll stop after this. The probability of exchanging information as a function of the state that you land on when you do information exchange, okay, is given here. It's really quite low until both of you are very high, and we know that at least if you're starting from the no information exchange state, you don't get very high very often. Is that clear? Okay. So it's true that often one firm will want to exchange information, but you need both firms to exchange information for the thing to work. Okay? So what's going on here? Why don't they want to exchange information? You're starting from a base case where there's no information exchange. You get to a point. At that point, they ask you, do you want to exchange information? Is that clear? But we know that at the point you get to, you're going to get to low state points. Okay? But we know at the point you get to, having no information gives you more profits than having much information. Because we showed you that at any given state, Is clear? The reason that you want to be given information states is the future states. But at any given state, okay, the profits are higher if you don't have information exchange, and that's because you're less aggressive. Is that clear? Especially in the low states, where you always hit it when you're starting from no information. Okay, so they're low states, and if you stayed with no information, then in the next few states, which are also likely to be low, you'd also get less profits. Is that clear? Until you came to the new state. If you did the new thing, if you started with an information exchange thing, you'd get lower stuff now. It's true that in the future you would get more, but there's going to be another choice in 4 periods. Okay? And you can't commit not to break that choice in 4 periods. There's no commitment here. Is that clear? And as a result of that, the short-term incentives are not to exchange information, even though it's in your long-term benefit, because you can't commit to it long-term. Is that clear what's going on? This surprised us a little bit, but when we understood what was going on, it wasn't such a surprise. But so commitment matters in these models, okay? That's really all I had to say. So I finished 3 or 4 minutes early. Okay, I skipped a bunch of stuff, but I'm happy to take questions, including on the stuff I skipped. Okay? There's a lot. Go ahead, shoot.
Excuse me, do we can change not to information, for example, send some cheat code or not?
In this model, no. The reason it's no is I've told you what information is sent out, and the information. It doesn't mean I couldn't have modeled something else. Okay, but what I model this way, I'm going to say one more thing in a second, but on this. But when I modeled it this way, I told you who was giving the information. It was the procurement agency. It was telling you who won the bid, what was the bid, okay, and we're assuming that it's. And I said in the beginning, when we do reveal the information, it's truthful. I want to say one thing about collusion. One more thing about collusion, which is, the standard Markov perfect stuff that Myrtle went over in the first lecture, it's easy to build collusion into this, okay? All you need to do is put a state variable there which says, if you're doing grid trigger price strategies, whether somebody deviated in the past, okay? The problem is you could do it in 55 different ways, okay? And that's the problem. Figuring out what's the appropriate way to do it in any given situation, to model the collusive behavior in any given situation, okay, is the problem, okay? That's it. I'm finished. And so after lunch or during lunch, if somebody wants to talk to me, I wasn't at the poster sessions yesterday very much. I talked to a couple people today, but it's all over for now.